Okay, so now we're going to do the 2023 AIME I problem number 4. Again, the solution that I'm sharing is what I did. I'm not utilizing a shortcut in this problem. I will show that shortcut at the end. Mainly, I couldn't think of the formula I wanted to use, or how I couldn't recall it off the top of my head. So I just calculated it, and it did a little bit bashy there. But there's kind of ways that you can shorten the process. We'll get to that part in a minute. After I'm done with that version, I will show you what the formula was I was supposed to recall but couldn't think of it off the top of my head, and I'll show you why it works. Okay, so the sum of all positive integers m such that 13 factorial over m is a perfect square can be written as this: 2 to the a, 3 to the b, 5 to the c. Basically all the primes that are 13 or less with an exponent, where a, b, c, d, e, and f are positive integers. Find the sum of those values. Okay, so the first thing is we probably want to prime factor this. I mean, if we're going to know that it's a perfect square, we kind of want to know if m is going to divide in, how that's going to happen. We need this to be prime factor so that we can determine how that's going to work. So we're going to use, I think it's Legendre's formula, if I'm saying it correctly. Legendre, I can never remember how to pronounce that word, that name. But basically, the formula is pretty simple, though. It's kind of common sense. You're going to divide 13 by 2, and that's going to tell you how many even numbers there are. You're going to round that number down. So you're going to get 6.5 rounded down will be 6. So that's going to give you all of the factors of 2 up until, just the evens that contribute 1. But now there's some evens that contribute 2, like 4 and 8 and 12. And so you're going to take another power of 2 for each of those. A quick way to do this, though, is just to take this number and divide it by 2, and you will get 3, and then just round down. So if I divide this by 2, you do it again, you're going to get 1.5, and rounded down is 1, and so altogether you get 10. Why does this work? It's kind of hard to explain in a short video, but it does work. Just remember to always round down. So 10 powers of 2, you're going to have 2 to the 10th. Then times, now we're going to do the same thing for 3. So for 3, it's kind of the same process. You're going to do 13 divided by 3, rounded down. That'll tell you all the multiples of 3, each which contribute at least 1. And so you're going to get 4 of those. 4 and 1/3 rounded down is 4. Again, same thing. You're going to divide the 4 not by 2, but by 3. And you're going to get 1 and 1/3, and you're going to round that down to 1. Again, that represents the number 9, right? 9 has 2 powers of 3 in it, and that's going to get you an extra power of 3. We already counted 3, 6, 9, 12 one time. Now we're going back and getting how many had 2 powers of 3. And if there was a 27, you would do 3 powers and so on. So you're going to have 5 total for this. So you have 2 to the 10th times 3 to the 5th times 5. And when you do 13 divided by 5, you're going to get 2 and whatever, some remainder, right? 3/5. But we don't care, right? So then we keep going. There's only going to be 1 power of 7, 1 power of 11, and 1 power of 13. Where do you learn this? You can learn it in Intro to Number Theory. From the Art of Problem Solving, they will go through and show you how this works and give you multiple problems from which you can practice the concept in motion or in play. So m equals this. Okay, great. Or not m equals, sorry, that's 13 factorial. Okay, then now what? If we're going to divide something into this and get a perfect square, you should know the form of all perfect squares. All perfect squares have to have even exponents when they're prime factored, okay? So because of that, like for instance, 4 to the 1st does not have an even exponent, but it's a perfect square because that's not prime. It's 2 squared, right? So just be careful with that when you're making that line of reasoning. That they are all primes. Okay, so we've got the 2 to the 10th. That's okay. We're going to need to take out at least 1 3. So this is, again, the way I walk through it. I'll show you the proper way at the end. If I take out 1 3, right, and then I take out the 7, the 11, and the 13, all of the values of m have to have this. 3 times 7 to the first times 11 to the first times 13 to the first. So m is going to have to equal that, possibly more added to the 3, and then we have to figure out what's going to happen with the 2 to the powers of 2 and the powers of 5. Because what we're looking for is the sum. Find the sum of all positive integers m. For a second I thought I didn't write the question correctly. I was like, where is it? It's right here. The sum of all positive integers m such that that is a perfect square. So we have to find all the m's. And every single one of those m's is going to have this. Okay? So that's what I did on my paper. I pulled this out. Now I said, okay, what's left after we take that out? Okay, what's left? We'll put left. Left we have 2 to the 10th, we have 3 to the 4th, and we have 5 squared. As it stands, this is a perfect square. Okay? So we should consider, we need to add up all of the types. And here's what I did. I couldn't think of the formula for how that process works. And again, we'll cover it at the end. But what do you do when you can't remember a formula? You just, oh, I don't know the formula, I can't do it. No, you're going to have to figure something out, right? You're going to have to figure it out. So what you should do is just, it's going to be kind of bashy, but you have choices for 2 to the 10th, which is actually the secret of how the shortcut process works, but I couldn't think of it when I was solving. But if you think about the 2 to the 10th, you could either have 2 to the 0, 2 to the 2nd, 2 to the 4th, 2 to the 6th, 2 to the 8th, or 2 to the 10th. Those are all your options. For 3 to the 4th, you could have 3 to the 0, 3 to the 2nd, or 3 to the 4th. And for 5 squared, you could only have 5 to the 0 or 5 squared. These are your options. So if you think about it, how many numbers would we have in here? We would have, add up all your choices. 1, 2, 3, 4, 5, 6 choices times 3 choices times 2 choices is 6 times 6 is 36. You would have 36 numbers in here. You got 12 minutes. If you really can't find a better way to kind of quickly go through that process, write them all out, I guess, right? I mean, might as well. That's 6, what is it? How many points? 10 points for an AIME question, right? 10 points. So it's just worth it, right? So if you had to come back and do that later when you ran out of problems you knew how to do, yeah, it is what it is. Okay, but that's not quite what I did. I said, let's just pick one of these, like 2 to the 10th. If I picked a case where I had 2 to the 10th, I want all of the m values that include a 2 to the 10th. So I just defaulted my selection to this one. Now, these ones then become what I have to match with the 2 to the 10th. So I just picked them all out. I said, well, I'll have 2 to the 10th with 3 to the 0, 5 to the 0. And then I'll have 2 to the 10th plus 2 to the 10th times. And I realized at this point, hey, they're all going to have a 2 to the 10th. Let me just keep that factored out. So rather than keep writing 2 to the 10th, I just took that out. And so I'm going to have, number 1, a 1. What's the 1 represent? 3 to the 0, 5 to the 0. Now I'm going to do 3 to the 0, 5 to the 2nd. So that's going to be plus 5 squared. Plus, then I'm going to do 3 to the 2nd, 5 to the 0. That's 3 squared. Then I'm going to do 3 to the 2nd times 5 to the 2nd. Plus 3 to the 2nd times 5 to the 2nd. Plus 3 to the 4th times 5 to the 0, which is just 3 to the 4th. Plus 3 to the 4th times 5 squared. Okay. Some people remark that it looks like I'm slanting my writing. It's because I'm looking this way trying to write from the side, but it does slant down a little bit. In order to write straight, I'd have to go like down like this and like look at the board and block the camera. It's really kind of hard to do if you've never done it before. So yeah, that's what's going on there. Sorry about that. Okay, so this is what you would get for the choice of 2 to the 10th. Doesn't it make sense that all of these choices would come out the exact same way? That I would have this parenthetical expression, and I'd have times 2 to the 10th, and I'd have the parenthetical expression times 2 to the 8th, and the parenthetical times 2 to the 6th, and so on. Well, then first off, let's just count what this is real quick, right? So you're going to have 1 plus 25 plus 9 plus, this is 15 squared, which is 225 plus 81, and you have 81 times 25, which is like having 81 quarters. You could also do 3 squared times 5, like think of it like this, 3 squared times 5 squared, right? Because just take out half of each of those powers and you'll get this. So 9 times 5 is 45, and 45 squared is 2025. If you thought of it as quarters, 80 quarters is going to be $20, right? Because every 4 quarters is $1, and you have another quarter, 2025. Think of it that way as well. Let's combine things nicely now, or for the most part as nice as we can. Let's do 9 and 81 makes 90. Let's add this one and this one. That's going to be 2,250, correct? Yes. And then we got the 90, and what's left that we haven't done anything with? We've used all but these two, 26. So we're going to add 26 to this, and let's see what we get. 2,340 plus 26 is 2,366. So we would have that. Okay, so again, think about what's inside. What's inside is 2 to the 10th times this parenthesis right here. Right? And that parenthesis is 2,366. Then you're going to have 2 to the 8th times this parenthesis, which is going to be 2366. Then you're going to keep going all the way down, plus ... until you get to 2 to the 0. So you're going to have 2 to the 0 times 2366. Okay, now, since that's recognized, why don't we pull 2366 out to go with all of these? And before we do that, let's just pause and ask ourselves, are we making any kind of mistake? Kind of second guess yourself, right? I've got all the m values here that have to be a part of every single m, right? And so what do all of these represent? They're all of the cases of m that have all of this and 2 to the 10th as the power of 2 selected. Because see, if I distribute this 2 to the 10th, I will get this one. And I'll have 2 to the 10th times 5 squared times all of these. And 2 to the 10th times 3 squared times all of these, right? And so then within that, we can see that all of our choices of 2 are going to have this. We feel pretty good. This is going to be it, right? So we're going to go ahead and take out, I'm going to have 3 times 7 times 11 times 13 times 2366 times what's going to be left in here after we factor that out? 2 to the 10th, 8th, all the way down. Let's just add that all up, right? 2 to the 10th is 1,024. You should memorize your powers of 2 up to at least 12. So 1,024, 2 to the 8th is going to be 256, and then 2 to the 6th is 64. You could just keep dividing by 4 as well if you wanted. So divide by 4 to get 16, divide by 4 to get 4, divide by 4 to get 1. Let's add this all up. This is 1,280 right here. This is another 80 right here. And so you're going to have 1,360 when we add that to this. And you got 5 more. You've got 1,365. Now there's something about that 1,365. Number one, 65 is a multiple of 13. So you're going to have 13 times 105. Because what are we doing here? It's 13 times 100 plus 5, right? Because you have 1,300 and an additional 65. And 105, of course, is 7 times 3 times 5. So this part right here is 13 times 7 times 3 times 5. Okay, so now what? Let's go ahead and migrate all of these over to here. And we still have this 2366 to break down. And we're hoping right now that it's powers that we like, because if it's not, we're in a little bit of trouble, right? So we made a mistake if that's the case. So you got 13 squared. I've got 3 squared. Okay, let's go ahead and write it here. 3 squared, 5 to the first. Your 7's going to pair up with this one to make 7 squared. The 13, we got an 11 to the first still. And the 13 squared. Okay, I'm going to erase some stuff here so we have some space and it's not so clustered. Okay, and get rid of that too because we don't need it anymore. Okay, so 13 squared. Now the 2366, we can break it down. First thing I'm going to do is there's definitely a 2 in there, and we don't have any 2's out here yet. So I'm just going to put the 2 here and make my life a little bit easier. I'm going to cut that in half. So 2,000 cut in half is 1,000, 300 cut in half is 150, 1,150, and 33 is 1183. So you're doing 1,000, 150, and 33. 1183. Okay, then what? The next thing would be, we got to guess about what's going to go in here. 11 doesn't go in, all right, because 1100 works, but 83 does not make a multiple of 11. Maybe 13, right? Let's just think. If this we did 1300 minus 117, that works, right? Is 117 a multiple of 13? Yeah, because it's 130 minus 13. This works. So you're going to have 1300 minus 130 plus 13. So that's how I thought of this when I checked it. It's the work I did on my paper, right? So you got 13, you get 100 minus 10 plus 1. So 91. You have 13 times 91 then, okay? This must be 13 times 91. Okay, then what's 91? It's 7 times 13. So you're going to get 2 more 13s. Your power is currently 2. We're going to get 2 more of those to be at 4. And the 7's going to gain a power as well, and you will be at 3. And so now we have all of the exponents that we want. 1 plus 2 is 3, plus 1 is 4, 5, 6, 7, 8, and 4 more is 12. What's funny is the moment of panic I have right here, because I solved it earlier and got 12, and I'm like, if we don't get 12 right now, I'm going to have to refilm the whole video because I must have made a mistake. Please be 12 right now. And it was 12. Good. So I didn't make a mistake up to that point. Now, we talked about a formula that could have made this easier. We also hinted at how that formula works. So I'm going to go ahead and erase probably all of this right now. Yeah, just to make some space, and I can show you how that's going to work. Because there is a formula that you learn in the Intro to Number Theory book that talks about the product of all positive divisors. And for a minute I thought, oh, is that what this is that we're doing? No, we want the sum of all of these things. But the formula is something along these lines. Basically, you're going to have a choice of all of these right here, okay? All of these right here. So if you think about it, what we're going to use is fundamental counting principle. We're going to need to select one of these, and one of these. This could be thought of like a polynomial. 2 to the 0 plus 2 squared plus 2 to the 4th plus 2 to the 6th plus 2 to the 8th plus 2 to the 10th. And then I would multiply that. I should have done it lower. I knew I didn't have enough space to write it with big stuff. Let's do it one more time right here. 2 to the 0 plus 2 to the 2nd plus 2 to the 4th plus 2 to the 6th plus 2 to the 8th plus 2 to the 10th. Now, if I add my powers of 3, let's think about what's happening here in just 1 second. Let's put this part, and then let's put this part. 5 to the 0 plus 5 squared. Why would this be the sum of all possible values within here? Why would this work? Because you're selecting one of these, and one of these. And you're doing every possible selection when you write the plus sign, right? Just like this. If I do A plus B plus C, right, times D plus E, you're going to get every combination. You're going to get A times D plus A times E. You're literally distributing to create that calculation. Then you're going to get B times D plus B times E and C times D and C times E. That's all of them. That's every single choice I could have made here with every single choice I could have made here. And we have 3 of these, right? So you have the first 2 would go off just like this, and then you would then combine that with 5 to the 0 and 5 to the 2nd to get every possible combination there is. And so if we would have known this formula or remembered how to do it precisely, I'll write what the formula is in a second too. It would have been a lot faster, right? But again, you're not too stressed. You got 12 minutes. This is not that bad. It's a little bit bashy, but you know, you just kind of have to live with what you got. So here we go. This is, again, so we already did, right? We added this up earlier, 1,024, 256, and then we had 64 and 16, which is 80, and you had 4 and 1, which is 5. And you added these, and you had 1,280, 1,365. So that's what that comes out to be, right? And what is this? This is everything in here. So you're going to have 1,365, which we already did, times, what's this? 81 plus 9 plus 1 is 91. And this is 26. 91 being 7 times 13, 2 times 13, 13 times 105, and we're breaking it down a lot faster if we have that. The specific way that the formula gets written, let's show that as well real quick. We might as well. Just so you can add it. You should have this formula in your small notebooks. If you don't know what the small notebook is, go look up the video on my channel where I explain why I recommend having one. First off, the prime factorization of a number can be written as, this is like the summation symbol, it's the pi symbol, and then you will write down below k, and you're going to have a prime sub k to the power of a sub k. So n, the number that, or m rather, could be written in this form, whatever m's form is. Okay, m would equal this. It's going to be, when it's prime factored, p for prime number k, and when does it stop? We don't know, however many that it has. That's why there's no upper limit. And this product thing works just like the summation. But rather than be a sum, it's a product. That's it. Summation is the one with the capital sigma symbol, right? That's summation. You're probably familiar with that. This we don't see too much at lower levels in math. You won't see it probably in your high schools at all. You will come across it in competition math occasionally. It's worth it to try to learn exactly how it works. It really isn't that bad though. Anyhow, why would this be the case? Let's just take what m is, right? M is going to be, let's just say we had this one right here. You got like a 2 squared times 3 to the third times 5 to the first. Let's just say this was a value of m. Whatever, we don't care. Okay, but this is the prime factorization. Notice it's the product of 2, right? And then this is your, it would be like, for this problem here, it'd be like p sub 1 and then squared. And then this would be p sub 2 cubed and p sub 3 to the first. So p sub 1 is 2, p sub 2 is 3, p sub 3 is 5, and the exponents are the exponents. But wait, isn't the k? Yeah, this 2 would be a sub 1, a sub 2, a sub 3. But that's just showing you that it's a product of every prime to its exponent. Pretty straightforward, right? Okay, so then what? Well, what we want is the summation of all of these values. So you're going to have, let me see if I can just look at it real quick because it's hard to remember off the top of my head. Yeah, you're going to have the product of the summation, and the product's going to start from k, just like it does here, and you're going to have a summation from k is going to equal, let's see, from the formula, oh, they've got, I don't know, they've got actually different. I'm looking at one on a website. It's got I equals 0, 2, and you're going to stop when you get to a sub k. Okay, so you're starting at this value of I. We'll see what it's going to connect to in a second. You're stopping when you get to the max exponent of your m values. Okay, fair enough. And then you're going to have your prime p sub k to the power of I. So think about what this is. Let's just create it really quick with what we had a minute ago, right? We had all these powers of 2. And so you essentially have your prime, well, if we didn't have restrictions, we had to have perfect squares. But essentially, let's say that, let's just make up a number, I guess. You're going to have 2 to the 4th times 3 to the 1st times 5 squared. Let's just say you wanted to add right? Every possible value of this expression. The sum of all divisors is what this formula is for, right? Then you're going to take, let's take this 2, which is your P sub k, your 4 is your A sub k, and what would you get? You would get 2 to the 0 plus 2 to the first plus 2 squared plus 2 to the third plus 2 to the fourth. That is the sum of all of your primes up to their max value. Their max value is the max value in the prime factorization of m, right? So we're getting a copy of all of these, just like we have right here. And then you'd have 3 to the 0 and 3 to the first, right? I don't have space there. 3 to the 0 plus 3 to the first. Why is it plus? And why is it a product? The product is this parenthesis times that parenthesis. Because after you exhaust all of your powers of your first prime, you move on to the next prime, right? The next prime being 3, and then you'd have one more product. Again, all of the choices you could make. 5 to the 0, 5 to the first, and 5 to the second. How do we know this is going to work? Because again, you're choosing one of each of these. You have to have all of your powers are going to be of the form, all of your factors are going to be of this form, A, B, and C. And you need to pick what the A is. That's this selection. Pick any one of these, combine it with any one of those, and combine it with any one of those. You will get a factor of m. And so you're choosing every possible factor when you do it this way. And since you're getting every single one, that's how the formula gets generated to give you the sum of all divisors. But for us, in our special case, we can just do it with these. We don't want the powers of 1 and 3 and stuff like that because we need to have perfect squares as our values when we're done. And so that's why we did it that way. And what do we get? Final answer, we had it, it was 12. Let's go ahead and move on to problem 5.